In this module, we will cover maximum a posteriori estimation. This is also referred to as MAP. What it involves is to model the probability distribution over the model weights. In the previous lecture, we have studied the difference between maximum likelihood estimation and maximum a posteriori estimation. Maximum a posteriori is one step towards Bayesian, where we try to also use some prior information. If you have some prior opinion about your model parameters, you tend to incorporate into your model. So it is appropriate for problems where there is some prior information, where a meaningful prior can be set to the weight, the choice of different distributions and model parameters. And for this, for our problem of estimating the model parameters of the Gaussian distribution, we need to start with providing a prior. And in this case, what we do is we assume the prior also to be Gaussian. So we assume that this term, the probability of the weights with respect to certain parameters alpha. So this is the precision of this distribution. Precision, so alpha is 1 over sigma square. This is also Gaussian. And we have this, the overall probability of the weights can be written as the joint probability of each of these weight parameters. We assume each of these, the prior over each of these weights to be Gaussian. So when we write the joint probability of the prior, it can be written as the product of each of these terms. So we have this joint, again, these are also, the weights are also assumed to be independent and identically distributed, which allows us to write it like this. And with some mathematical manipulations, we can go ahead with writing, so we put the Gaussian equation here, and then we multiply each of these terms. So we have this product of alpha over 2 pi. So alpha is 1 over 1 over sigma square. So that's why we can write it like this. And similarly, again, we assume this to be have mean 0. So we have 0 minus this term. So you will obtain something like this. And when we multiply these terms, what we get is alpha over 2 pi. If we assume that our model parameter has mth order polynomial, it's going to have m plus 1 parameters. And what we then have is, so this m plus 1. So we get alpha over 2 pi. This is m plus 1 times. So that's why we have m plus 1 by 2. And then what we have is e raised to this term. If we multiply the m plus 1 times each of these, we get wi. So we have w1 square plus w2 square, w3 square up to wm square, and that can be written as an inner product of w vector. So we have w transpose w. If you check, it will be similar to multiplication of these terms. So that's how we express the prior distribution. And as per the Bayes rule, we can write the posterior over the weights given the data and these parameters. It can be expressed as the likelihood function multiplied with the prior. And then we have this normalizing term below. And this is just the evidence scaling term, and this is independent of the weights. So we can express the posterior as directly proportional to the likelihood function and then the prior. And in maximum a posteriori estimation, what we do is we want to maximize this left-hand side term. So we want to identify the values of the weights for which this term is maximized. And that would be equivalent to writing it like this. And again, since we want to pose it as a minimization problem, we put this thing as argmin of minus times minimization problem. And we also want to minimize the logarithm. So we put it at minus times log of this function. Now, let's try to compute the map solution. What we do is we want to identify the values of w for which this function is minimized. So we put it like this. And then, so this term, let me go back and try to explain how it comes in. So we want to minimize this, and this is written as, so we have these two terms, right? If we are going to minimize this, we want to minimize the product of these. And in the minus times logarithm form, these will be minus times log of this. And then again, the product can be split as an addition. So with the minus, it becomes again negative. So minus times log of this minus log of this term. And if you look at log of the prior, this term would imply taking log of this, and log of this can be written as log of this term and then log of exponential of this term. So log and exponential will cancel. So this will have this term left. putting all this here, what we get is minimizing the log of my negative log of the likelihood function, this term, plus this term. You can go back to the previous slide and check. You will obtain the log of the prior distribution to be as alpha over 2 W transpose W. Now, this part we can write it as using the Gaussian distribution. We take the log and then we put it here and we obtain this mean squared error scaled by beta. We have also seen this in the previous module where we were trying to estimate the maximum likelihood solution. So this is, it comes out to be here, and then we put this again, this term here. So that's our solution for maximum a posteriori estimate over the weights. And what we see here is this solution is equal to mean squared error plus an additional regularization term. So when you try to minimize this entire function, what you need to also have is to minimize the inner product of the weights. So this function does not let your, so this function tries to minimize the values of the weights themselves, thereby adding an implicit regularization. If you have done some machine learning already, or if you have done some just simple curve fitting as well, you might have seen that we empirically add this term and call it as a regularization in the maximum likelihood solution, maximum likelihood estimation type of solution. We add this regularization term to avoid overfitting. However, when we are doing maximum a posteriori estimation, this regularization term is already there. What this means is that the map solution has implicit regularization, and we don't need to explicitly regularize it anymore. Now, once we estimate these values of W map, what we have now is we have a Gaussian distribution like this. We have this joint probability distribution, so the distribution, and it's also referred to as predictive distribution. So we have now a predictive distribution with W map. And for new samples, if you are given some new samples to estimate the output, it can be written as like this.